integration and how to do it. Here we go. Should we start with indefinite or definite? Definite. Okay, I don't think you knew what you're voting for, but here we go. The one we did was definite, right? This is these are example of a bunch of definite integrals, right? We will. We'll cover both today. So remember, I gave you the fundamental theorem of calculus on Monday, yes? Where I said it was that big definition that said you basically find the antiderivative and then plug in the two methods of integration and subtraction. Does it sound familiar to anyone? I'll put it up here so we can see both at the same time. So the fundamental theorem of calculus says that if you so the integral of f of x dx from a to b is equal to capital F of b minus capital F of a. That's the fundamental theorem. That's the second part of the fundamental theorem of calculus. Okay, so, and the relationship between capital F and small f is capital F. If you take the derivative of capital F, you get small f. Right? AKA, this is the antiderivative of that. This, you undo the derivative. Okay? So remember this, I've been saying for a while now that we're going to spend this whole quarter undoing what we did last quarter. We did a bunch of derivatives last quarter, now we're going to undo a bunch of derivatives. So, and I told you guys to practice your derivatives because if you know your basic derivatives, it'll be a lot easier to undo them, right? Okay? So hopefully you've been doing that. So when I look at this thing here, this says that I need to undo the derivative of 2x minus 1. So I need to ask myself, where did these things come from? I took the derivative of something and got this. Right? Mm-hmm. I took the derivative of something and got this. That's the key. So then I have to think about what kind of derivative rule did I probably use in this case? Probably a power rule, right? Because it's just a straightforward polynomial. So that means that the derivative here, well, I did not leave much room here. I'll just make it really big. This probably came from x squared minus x, didn't it? Okay, now we just got to make sure, does that give me the right derivative? If I take the derivative of this, does it work? What's the derivative of x squared? 2x. Ooh, nailed it. What's the derivative of negative x? Negative 1. Boom! That was easy. Yeah? Of course, this is a definite integral, so I'm not done yet. I draw out a little line here and I put a 0 there and a 3 there. That tells me I got to evaluate these things at 0 and 3, yeah? So then I put a 3 in for x squared, and that gives me 9. Put a 3 in for x, and that gives me 3. Put a 0 in for x, that gives me 0. And put a 0 in for x, and that gives me plus 0 because it's a minus a negative x, right? So I end up with a total of 6. Okay? Yep. Isn't that slick? That's my answer. 6. Done. Boom. Yes. That's a good question. No, that's a good question. Let's see if it comes up. So number 2, 4 minus x. Where did that derivative come from, do you think?
4x minus x squared.
That had to come from 4x minus x squared, didn't it? But this time when we go to take the derivative to check it, we got a problem, don't we? What's the derivative of 4x? 4. What's the derivative of negative x squared? Negative 2x. Oh, missed it. So can I do something to this?
Divided by 2.
Oh, if I just put a 1/2 on here, that would take care of it, wouldn't it? Because then when I multiply by 2, 2 times 1/2 would take care of the problem. But the problem right now is it's producing an extra 2 that I don't want. So if I put a 1/2 out front, that'll take care of the problem. Okay? Now let's check it one more time. What's the derivative of 4x? 4. What's the derivative of negative 1/2 x squared? Negative x. Ah, it works. Okay. So then we just need to evaluate this from 0 to 2. So if I put a 2 in there, that'd be 8 minus, put a 2 in there, 2 squared is 4. 1/2 of 4 is 2. Put a 0 in there, and I get minus 0 plus 0. And I get a total of 6. Whoa, are they all 6? That's kind of weird. Okay. I think we've done this enough. We're going to switch gears to the indefinite, and we'll come back to this. So what is an indefinite integral? Notice all these integrals. So I would have given you copies of these, so everyone have them in front of me. But for some reason, no faculty could print today. There's an email that was sent out at 11:30 last night that for some reason the faculty print server is down, so no professors can. Students can still print apparently, but professors cannot. So some kind of a it's posted on campus. Yeah, so you'll have to print it off later. So. This says find the general antiderivative f of x plus c for each of the following, okay? So the idea here is, this is some function that I want to undo the derivative for. So it's the same thing we're just doing, I don't have the integrations in front of it, right? So basically what this is saying is, what is the integral, the general antiderivative? In other words, what's the integral of 4 dx? Okay? So, where did 4 come from? 4x. If I take the derivative of 4x, do I get 4? Good. Okay. But notice there's no limit of integration, so there's nothing to plug in. So the fundamental theorem of calculus doesn't really help me here. So we have to go back to the first part of the fundamental theorem of calculus, and it tells us that if you take a derivative without any limits of integration, you're looking just for an equation, not a number. You know what I'm saying? So we're looking for something just like, remember, when we're taking derivatives, sometimes we take the derivative and plug in a number. We don't know what the slope was at that point, right? And sometimes we just wanted a general equation, so we just take the derivative and leave x as x. Yeah? You with me? So that's what we're doing here. Now the problem though is there another equation that if I took the derivative of it, it would give me 4? What's that? 4x plus 2 would work, wouldn't it? So what's the derivative of 2? 0. How about 4x plus 3? Yep. How about 4x plus 7.8?
Yes.
4x plus pi?
Yes.
Yeah. So I can add anything I want out there, couldn't I? So when I say just find the general formula for this, well, that's a little bit tricky because there's an infinite number of formulas that could be that. Yes? So the way we combat this, and this is really important because you're going to lose points if you don't remember it, is whenever we take an indefinite integral, we just have to put a little plus c out there. Meaning that, and of course c represents a constant, right? So we're just saying it could be any of a family of equations that begin with 4x and end with a constant. So this is a linear equation with a slope of 4 and the y-intercept is any number you want. The whole family will work in this case. So when we take an indefinite integral, we're actually looking for a family of equations. And it's always from the plus c. There's nothing else you can do, right? There's no other way to come up with take the derivative and get 4 other than 4x plus a number. You with me? That's all we have to worry about is putting a little plus c out there. So on all of these questions on this worksheet, you're always going to take the derivative, take the integral or the antiderivative, and then put a little plus c at the end of it. Okay? So let's do another one. Yeah, because like this one here we're about to do. So let's integrate from our 2x minus 4. So in other words, we're just looking for the antiderivative, yeah? You got to put a little parenthesis here and a dx. You always have to have a dx or it doesn't make any sense, right? Because that's that little width to change in, right? So let's
do the antiderivative. What's the antiderivative of 2x? That must have come from x squared, yes. How about the antiderivative of negative 4? Where'd that had to come from? It had to come from negative 4x. Let's take the derivative and make sure it works. What's the derivative of x squared? 2x. Woo! What's the derivative of negative 4x? Yeah! So then we just need to put a little plus c there. Well, yeah, I'm sorry. Yeah, I wasn't really listening to you. I was thinking of right here. I thought you reminded me to put parentheses here. Yeah, the plus, because we're adding, we don't need parentheses, right? Because the add can any order, yeah. All right, how about this one? Oh, this one looks a little bit tricky. So we want to integrate 3x squared plus the square root of 2. Is that tricky? No, not really. Square root of 2 is just a number, right? Shoot, I thought we had a tricky one. Okay, so where did 3x squared come from? Had to be x cubed, didn't it? Because we're looking at the power rule, it's always got to be one higher than what we got, right? Because that's how power rules work. You drop the power 1. And where did square root of 2 come from? Had to be square root of 2x, doesn't it? Because that's just a number, yeah? So what's the derivative of x cubed? 3x squared. Woo! Not quite as exciting this time. What's this derivative of square root of 2 times x? Square root of 2. Yeah. And we put a little plus c there and we're done. Let's see if we can find an interesting one. Or more interesting. Ooh, how about this one?
Oh. We can't see the fraction line on that one.
Oh, you can't? Oh. This is a new type of powers. You raise to a third power in one level and then a second power. Okay, anyway, this is 2/3 power, yeah. There's a fraction bar there you can't see. So where did that come from?
Oh, good.
Don't we just add 1 to the exponent? Isn't that all we're doing? Because that's what you do when you derive. You take 1 from the exponent, right? In the power rule. So this had to come from x to the 5/3 power. Yes? Because 2/3 plus 3/3 is 5/3, right? Don't put 1 and 2/3 up there. That's just going to mess with you. Okay? So now if I take the derivative, that's not going to work because it produces an extra 5/3. Yes, I just need to put a 3/5 out front. I see a pattern developing here. Seems like in the power rule, we just always raise the power 1, and then we put the reciprocal out front of the new power. Does that make sense? Yeah? But I don't always just automatically do that. What I do is I just get the power right and then check the derivative and make adjustments. I think that's probably the better way to do it. Everyone understand what I mean by that? Just add 1 to the power, take the derivative, and then make the necessary adjustments so that it comes out right. Okay? Are we done here?
No, let's see.
Yeah, good for you. Let's see. Okay, so these are all power rules here, aren't they?
Probably.
Let's do one really complicated power rule. 18. Whoa, that was weird. It's really complicated. It's so complicated my pen can't handle it. You can't handle the truth. Okay? So where did 18x to the 8th come from? What is going on here? So that had to come from x to the 9th. And if we put a 2 out front, that would give the right 18, wouldn't it? Because 9 times 2 is 18. So you guys are already doing these in your head. You're always all worried about them. And so this had to come from x to the 5th. And what do I need out front? 5. And this had to come from x to the cubed. And what do I need out front? Nothing. And then plus c. Piece of cake. How about this one? Should we make a little adjustment to this before we take the integral? wouldn't it make more sense to write this as 4x to the negative 5 minus 3x to the negative 4? What is going on there? Why does it keep doing that? Everyone understand why that would be helpful? So now it looks more like a power rule. Yeah? So then when we integrate that, now be careful here, this had to come from x to the negative 4, right? Because when I add 1 to the power, it actually gets smaller in the sense negative. Yeah? And that means, what do we need out front? Negative. Need a negative, don't we? And then this had to come from x to the negative 3. And we probably need a plus there, don't we? And then a plus c. It does, doesn't it? I think you're almost there, aren't you? Okay, how about this one? What adjustments should we make to this before we try to integrate it? You got to divide that x to the fifth in there, right? Remember when you have a bunch of things on top, bunch of terms on top and one term on the bottom, you can just divide the term on the bottom into each one? Or you could break that into 3 fractions with x to the fifth as your denominator, right? Because there is no quotient rule in integration, right? Because we'd have to use the quotient rule otherwise, but there is no quotient rule in integration. So what I'm going to do is I'm going to rewrite this as the integral of 4x. Everyone see where 4x came from? Plus 3, period. I was about to say something else, but I wasn't done that. Minus 8x to the negative 5 dx. Okay? Any questions about that adjustment? So then we integrate it. This had to come from x squared. So I probably need a 2 out front. This had to come from 3x, no adjustment. This had to come from a positive x to the negative 4. So I need a 2 out front. And then a plus c. So that's the power rule. You just did the power rule backwards about 5 and 6 times. Weird, huh? Yes. No offense, but I hate those kind of questions. Find the general antiderivative. I guess you don't have to. Right. My direction just said, give me antiderivative. I don't have to say show your work. I just have to ask the question the right way. Okay, so let's try a couple more complicated ones here. These are all power rule ones. Let's see. I might have to go back to the definite integral one to get the more hard ones, more difficult. But let's look at that. How would you do number 16? Just not doing it, but just think out loud, somebody. Yeah, you'd have to multiply it out because we don't have a chain rule in integration either, right? If this is derivative, it'd be easy. You just multiply the front by 2, drop power 1, times derivative inside, boom, you're done, right? But there isn't. Well, we don't have a technique like that. There will be a technique like that that's not precious. It's a little bit weird, but so really the only way to handle this right now would just be to multiply that out. So x squared plus 1 times x squared plus 1, you get a big long, 4-3 polynomial, right? And then you just integrate all of the electrons. Okay? Okay. So let's hop over. What? Okay, let's hop back over here. Let's get serious now. Okay. How about number 7?
At first glance, you think, oh, I'll just write it as x to the negative 1. So then when I go to take the antiderivative, what do you get? X to the... I don't think that's right. So now we have to go back and think about our derivatives a little bit more carefully. So you've been practicing your derivatives, right? Your basic derivative, yes? No, go for it, yeah. Yeah, that's just natural log, isn't it? Remember the derivative of ln x is 1 over x, right? So you see how I've said you need to be practicing your basic derivatives? Because if you haven't been practicing basic derivatives, you would have no clue what to do with it. Yeah? But since you all have been practicing your basic derivatives, and you have probably in the last couple of weeks have done this, I don't know how many times, where you've looked at this and said, oh, y equals ln x, take the derivative of that, y prime, oh, that's 1 over x, oh yeah, I remember that. Or y equals ln 2x, oh yeah, the y prime, that's 1 over 2x times the derivative of 2x, which is times 2. Oh, so that's just 1 over x. Weird. Okay. Or y equals ln x squared. Y prime is 1 over x squared times the derivative of x squared, which would be 2x. So that's just 2 over x, isn't it? Right? You've been doing something like that? Because you've been practicing your derivatives? Of course, Mr. Dale, because I want to be successful in this class. So, what's this? This is just going to be natural log of x evaluated between 1 and 2. Yeah, I should have higher expectations for this class because this is my best class ever, right? I just have so many times told people to practice and they ignore me until I bring it up. Like, oh wow, I guess I should have practiced. Now I see why. I should have listened to him a week and a half ago. Okay. So here we got the same idea, 1 over x. There we got dt over, that's still ln t, isn't it? Okay, how about e to the x? Now this one, oh man, this is where, if you haven't been practicing, you're in serious trouble. Right? I took the derivative of something and got e to the x. What could it possibly have been? Yeah, that's just e to the x. Evaluated from 0 to 1. Right? Because you remember the derivative of e to the x is e to the x. That's our favorite derivative. Okay? Of course, I'm not finishing these. To finish this, you go e to the first minus e to the 0, right? What's e to the 0? 1. So this would be e minus 1, wouldn't it? Okay? Ooh, what about sine? The antiderivative of sine. Yikes. Well, sine comes from cosine, right? But what's the derivative of cosine? Negative sine. So that means I'm going to have to put a negative cosine out here. Yeah? Because that way the derivative of negative cosine would be positive sine. Yep. And I'm going from 0 to pi. What's cosine of pi? It's negative 1, isn't it? So that'd be 1 minus, what's cosine of 0? One, so that'd be minus a negative 1. Yeah, but you had an excellent teacher, so you have no excuse. Oh, this one's tricky, even though it's an e to the. So this has to come from e to the negative t, right? Because e to the u, the derivative of e to the u is e to the u times du, right? So what is, if we take the derivative, do we get the right answer? Not quite. Because the derivative of this is e to the negative t times the derivative of negative t, which is negative 1, right? So if I take the derivative of this right now, it's going to kick out a negative. Do we want a negative? Nope. So we need to put a negative here. That way when it kicks out a negative, the negative cancels each other out. Okay?
Which let's explore that a little bit. So in general, if I go the integral of we'll do it back to the indefinite integrals, e to the 5t dt. Come on. E to the 5t dt. Okay? So that's got to come from e to the 5t. We all agree with that, yes? But now if I take the derivative, that's going to be e to the 5t times the derivative of 5t, which it's going to kick out, the chain rule is going to kick out a 5, isn't it? So this is kind of like the power rule. We have to make a little adjustment. So what do we need to put out front? 1/5. And then plus c. Okay? We doing okay? Well, that seems impossible. Secant squared? Oh no. We're going to have to do like a chain rule or something? I don't know what to do here. Oh, wait a minute. Isn't that the derivative? Exactly? Oh, it is. So if I want to undo this, that's just tangent theta plus c, period. Yeah? What if it said integral of secant squared 2 theta? Well, that's just tangent 2 theta, right, plus c. But if I take the derivative right now, I'll get secant squared 2 theta with an extra 2, won't I? So I got to put a little 1/2 out front. Okay? So if you go back to the derivative practice module, at the very top of it is a basic generic list of what I call the basic derivatives. So what you need to be responsible for going forward, getting better and better at, is knowing the antiderivative of all those basic derivatives. Does that make sense? And some just simple chain rule iterations. That's what I mean by it. See how this is the chain rule iteration? So this is just a normal basic antiderivative. This makes it a little bit harder because there's a little chain rule kick out in there. The number. So the chain rule iterations will always have it'll just kick out a number. When it starts kicking out some other numbers, we gotta come up with a new technique. We'll get to that later. But right now, you should be able to handle when it kicks out your little number. Yeah.
That's something inside the principle of the chain. That's what you have.
Right. When you take the derivative of tangent of something, you get secant squared of something.
Yeah, that's something to take that.
Sure. Never changes. Okay. Any other questions or comments about?
Let's see if there's some good ones here that we missed. Don't want to miss any of the good ones. Uh-oh. Tangent. See number 20 down there?
Yeah.
Tangent.
What's that? We haven't learned that.
Is tangent the derivative of anything?
Secant squared.
No, tangent, the derivative of secant is secant tangent, right? But tangent isn't the derivative of anything, is it? Ah, so that one's maybe a little bit out of I didn't see it. I flipped it out. Might have to do good substitution stuff.
How about number 21? You guys have any clue what to do with that?
That looks like Trey.
Kind of just stated that it's been a while ago. It's got to be squared, doesn't it? Maybe we could do this.
I can see what it is.
Remember doing this in trig?
Oh, not that.
Well, the whole purpose is to turn that bottom into cosine squared, right? Because 1 minus sine squared is cosine squared. Yeah. So then you really have cosine theta minus cosine theta sine theta all over cosine squared theta. And then you could possibly do some canceling there and stuff. Okay, well, anyway, what you want to do is get really good at the power rule in reverse, making the necessary adjustments. The sine, cosine, tangent, secant, cosecant, all those derivatives, right? The exponential, I guess we should do a quick exponential one. So let's say that I want to integrate, 2 to the x dx. Well, that's got to come from 2 to the x, right? It's got to come from 2 to the x. But remember, when you take the derivative of 2 to the x, you get 2 to the x times ln2. You remember that? So this is going to, it's not the chain rule kicking out now, it's just the normal rule. This is going to kick out an extra ln2 when I take the derivative of it, right? So that means I need to divide by ln2 here. Let me be abundantly clear here. When y equals 2 to the x, y prime, in case you've forgotten, is ln2 times 2 to the x. Remember that? So when I integrate 2 to the x dx, I get 2 to the x with 1 over ln2 to counteract that thing plus c. Right? Oh, I think we're done now.